Okay, so with that, let me begin. So today we are happy to have a colloquium by Vinicius Duarte. Vinicius got his education in Brazil at the University of Sao Paulo, where he defended his PhD thesis in physics in 2017. And then he received the Brazilian Physical Society Thesis Prize for this work. Then he went to Princeton Plasma Physics Lab, first as a postdoc, and then became a research staff member in 2020, and he's there now, of course. Vinicius is a member of the ITPA Energetic Particle Physics Topical Group, and is also on the editorial board of the Physics of Plasmas, and on the executive committee of the Transport Task Force. In 2023, so just this past year, he received the Department of Energy Early Career Award. So congratulations, to study fast ion transport in tokamaks. And in general, he is an expert on the interaction between energetic particles and Alfvén waves in fusion devices. Today, I guess we'll see some sort of mixture of that research with astrophysics. So the title of today's talk is on the self-consistent reduced transport theory for discrete modes with applications to resonant dynamics in plasmas. I presume that means fusion plasmas, but we'll see. And in galaxies. So with that, please go ahead and get started.
Well, thank you very much, Dmitri. Appreciate it. Thanks for the invitation to give this colloquium. So let me thank my co-authors, Jeff Letts, who is a joint main author of the paper I'm going to describe, Chris Hamilton, that helped a lot with and actually led the application of this work to galaxies, Nick Pham, who's a PhD student at PPPL, and Nikolai Gorelenko. Okay, so I'll be talking about a formulation, a reduced formulation that I think is transparent enough and offers interesting physical insights of how the redistribution or the transport of particles upon their interaction, the resonant interaction with discrete modes happen. And I'll show how the same framework can be applied not only to plasmas, but to the resonant dynamics of stars and dark matter in galaxies. Okay, so in a nutshell, let me try to convey my motivation and the main results. So we're going to be looking at wave-particle interactions, and I'll make the case that they can be very sensitive to collisions, even though the non-resonant dynamics is not that sensitive to collisions. So this is a fundamental plasma physics problem. Those types of wave-particle interactions happen everywhere. And I'll be talking about those two applications that I just alluded to. In fusion, I'll be mostly showing results for energetic particle transport in tokamaks, and in galaxies towards an understanding of radial migration. So we want to understand the influence of collisions on particle transport as a result of resonant interaction with discrete instabilities. So let me clarify what I mean by discrete. Many people, for example, working on turbulence, they're used to a dense spectrum of waves that are always overlapping. Here we're interested in modes that might overlap with one another, but they might evolve by themselves. So they're countable. And moreover, what allows for a lot of analytical simplifications is when they are marginally unstable or near threshold. The main results are that near this instability threshold, a quasilinear transport equation for the distribution function naturally emerges from nonlinear theory without any other assumption. And I'll show that collisional scattering broadens the resonances, while dynamical friction or drag leads to shifting and splitting of the resonances. Okay, so that's the outline. I'll the first part, the first bullet is the bulk of the most slides of my talk. It's towards establishing the transport framework for the transport of those particles interacting with those discrete modes. Then I'll show comparison of this developed theory with nonlinear simulations and the two applications I mentioned, and lastly, summary and implications. Okay, so I talked about energetic particles are one of our main motivations is to try to understand how those energetic particles behave in fusion devices. So to make fusion happen, we need to confine those particles really well. They cannot escape the device, otherwise they melt the walls and they cool down the plasma. You cannot sustain a burning plasma. Those energetic particles are mostly result from radio frequency heating, neutral beam injection. They can be the fusion products, the alpha particles, and they can be relativistic runaway electrons. What I'm showing here in this picture is at the center here is the National Spherical Tokamak experiment, upgraded here at the Princeton Plasma Physics Lab. That's what you see in the center. And what you see circled in white are the neutral beam injectors. So you can tell they're very big, and the radio frequency antenna system, which is even bigger. So they comprise much more area in the lab than the tokamak itself. Last week you heard the JPP colloquium on alpha particle in jet. So this is kind of related to that. Now, we want to understand the confinement of those energetic particles, and it so happens that they can resonate very strongly with discrete gap modes, namely alphenic eigenmodes in toroidal devices. So what I'm showing here is a sketch of how those modes show up. They were predicted by this 85 paper here. So the toroidal periodicity induces gaps in the frequency space, the same way that in a semiconductor, the periodicity of a lattice can induce gaps in the energy spectrum. And those modes, this is the plot on the right, is the eigenstructure. They result from coupling between neighboring poloidal harmonics. Those modes live in the gap, so they are very weakly damped. That's why they can be very dangerous, and they have a resonance that with those energetic particles that can drive those modes unstable and eject the energetic particles from the device. So again, unlike in other contexts, like in turbulence modeling, the modes here are discrete in nature, and the resonances can be isolated or overlapping, and they might dynamically switch between one scenario and the other. That's why we need to develop models for those single modes, or even better modes, models that work for single isolated modes, but also cover the overlapping regime. By the way, I'm not seeing the raise hands or the chat, so please do interrupt me anytime throughout the presentation.
Yes, I'm monitoring that.
Okay.
Right.
Thank you.
Mm-hmm. Something
right.
happens.
Yeah. So let me introduce like the basics of the resonant dynamics that we're going to need to develop the framework for this colloquium. So this is the textbook presentation of what a inverse Landau damping is, or which takes the form of the so-called bump on tail distribution. So that's the simplest illustration. You have a distribution function that depends on velocity. The bulk plasma has something close to a Maxwellian, but then you inject a beam which form this bump on the tail, and you might have resonances that lie on the positive gradient region of the distribution. So that means free energy for the instability. And if you have this resonance here, then particles will open up an island around that resonance. So this resonant velocity here would be the center of this resonance. This is the phase space portrait. Particles would differentially phase mix here, and eventually you'd get some degree of flattening around the resonance. And what happens to the mode that evolves at the expense of that free energy is that the amplitude will grow and eventually saturate. So that's the textbook picture, and we're going to build on that. So for simplicity, we're going to use position and velocity variables in this talk, but all the results are readily generalizable to action and angle coordinates that we need to treat a real toroidal device. We have three mechanisms at play here. We have the wave growth rate, which I'm gonna refer to in this talk by gamma linear. That's the linear growth rate, which is proportional to the local slope of the distribution function around the resonance. Those discrete modes, they can experience background damping rate, which is not related to the minority species, is some other sources of damping of the wave energy to the background plasma. That will just be a constant number here for simplicity, gamma D. And then we have the collisional drag and scattering rates that I'm going to refer to as alpha and nu, drag and scattering. So collisions will have an effect on eroding this plateau, and collisions might restore the local distribution function around the plateau and provide even more free energy for the distribution, making the system able to access different saturation levels. Okay, so how does collision enter in this dynamics here? So what I want to point out is that resonances are very delicate and they occur within very narrow layers. And it so happens that even if the non-resonant dynamics is not affected by collisions, the resonance can be highly affected by collisions. And the way to understand this is, so if we think of a very hot plasma, then the resistivity is inversely proportional to temperature to the 3/2 power. So the hotter the plasma, the less resistive it is. However, when we look at this global dynamics, so for example, in a textbook, a good quantification for how collisions are important would be the 90-degree pitch angle scattering rate, which is the characteristic rate at which particles are deflected by a characteristic angle of 90 degrees. However, resonances are so thin that you only need to kick a particle by a tiny fraction of a degree for the particle to cross the resonance and have an effect on the resonance. So because the resonance is so narrow compared to the, let's say, the macroscopic dimensions of the plasma in velocity and position space, you don't need that much of a collisionality to have a substantial effect on the local dynamics of the particles around the resonance. And that is quantified, that has been appreciated over the years by multiple authors. And a good quantification for this, the effective collisionality around the thin resonance would be by this nu here, which is the effective collision rate, which has this dependence on the 90-degree pitch angle scattering rate and the mode frequency. And in fact, numerical evaluations using the NOVA K code, they show that this effective collisionality is typically, for typical tokamak scenarios, can be usually 2 orders of magnitude larger than the 90-degree pitch angle scattering rate. So that's why collisions can matter a lot around resonances. Okay, so the crux of my presentation is shown by this slide. Let me try to unpack it. So the starting point here is the usual kinetic equation. So you see here the familiar, I mean, without the the right-hand side, we would call this the Vlasov equation. This is the mode amplitude, which is being referred to using this bounce frequency. In astrophysical context, usually this is called the libration frequency. So this is, when we look at the resonance, that's the frequency of a particle that is deeply trapped by the resonance to complete one bounce around the elliptic point. And it is proportional, this omega bounce squared is proportional to the mode amplitude. So nothing out of the ordinary here. So basically you can think of this as just the mode amplitude. In an electrostatic case, this would just be the wave electric field. On the right-hand side, we have the scattering operator and the drag or dynamical friction operator. So one is second-order derivative, the other is first-order derivative. And what's in front of them are just constants because we are evaluating this complicated collision operator locally in the resonance. So the resonance, again, is very thin, and we are evaluating everything at the resonance. So those are just constants here. In the 90s, Burke and Breisman, they discovered many interesting aspects of this collisional resonant dynamics that I'm very fond of, and they realized, among other things, that sufficiently near marginal stability. So let me just go back here for a while to define better what I mean by marginal stability. So we have this growth rate here due to the gradient of the distribution. You have the damping rate that is due to the background. A marginal unstable mode would be when the linear growth rate just exceeds the damping rate. So this number here would be just above this one here. So they realized that for those near marginal stability modes, this parameter emerges. So basically the bounce frequency, which again is this frequency of rotation here in phase space, proportional to square root of mode amplitude, divided by the effective collisionarity, is a small number. So they realized that, and they did perturbation theory on the kinetic equation. And that allows for the integration of that kinetic equation to any order you want in this small parameter here. That's the epsilon. And then they found evolution equations and everything. This is very insightful, and I'm not showing the equations here, but you can also understand what happens to the distribution function, and they become time-delayed integrals. What we realize now is that, and that's a new part, is that close enough to marginal stability when this number is small, we get more or less for free this other expansion parameter in which the effective collisionarity is much higher than this number, which is assumed is small. And what happens is that physically, when the effective collisionality of the particles that are in resonance exceeds the time scale for the net growth rate, which is this number here, it means that particles are kicked in and out of the island much faster than the time scale for the wave growth. So you start destroying this fine filamentation structure here, because collisions are just leading to memory erasure. So what it means that I said that using the Burke-Breisman expansion, you get the distribution function in terms of time-delayed integrals. What happens when we impose this other constraint here is that memory erasure means that only the time local dynamics matter. So the time delays become unimportant, and we can explicitly integrate, perform those integrals. So again, I'm trying to explain this in a simple form to illustrate the point that sufficiently near marginal stability, those two small parameters emerge, those two orderings emerge, and this general kinetic equation, nonlinear kinetic equation, becomes of this form here. So I'm not imposing any other constraint other than near marginal stability with those two orderings. Then this equation is naturally cast in diffusion form. So you can see that the partial derivative with respect to time remains, but the other terms become a second order derivative here with a diffusion coefficient here. And also the right-hand side becomes the same. So this is a form of resonance-broadened quasilinear theory, but very different from the ordinary Dupré form that was invoking a dense spectrum of waves. So this is, again, the dynamics for one single mode, even for one single resonance of that mode. And what is happening physically is that in the absence of collisions, we would have a phase space portrait like this. Collisions are destroying a lot of the phase memory and destroying that structure to the point that it becomes nearly isotropic in position, and only the gradient in velocity matters. Because the gradient in velocity is what we started with in the first place, but it does destroy the elliptic filamentation structure. So let me show the resulting set of transport equations, and those were derived independently by our group and by Peter Cato and later Cato and Tolman, using slightly different assumptions. So I'm repeating here the same equation that I just showed. That's the relaxation of the distribution given in terms of this diffusion term here and the collision term on the right-hand side. What emerges from the calculation is not only that your transport equation becomes a quasilinear theory with broadened resonance, but also it gives the answer to what is that broadening function. So this diffusion coefficient here, this is the form of it. And where nu, again, is the effective scattering frequency, and alpha is the effective drag or dynamical friction coefficient. So this equation for the relaxation of the distribution is supplemented by the evolution equation for the mode amplitude. Recall that omega bound squared is proportional to the mode amplitude, and it evolves according to this, where this is a growth rate that now depends on time minus a damping rate, where the growth rate is given by this. So again, it is similar to the usual inverse Landau damping picture in the sense that the growth rate is still proportional to the local gradient of the distribution function, but now it's a weighted function according to this diffusion coefficient here. So initially, you're going to have simply exponential growth, and then as the distribution relaxes, you start changing this growth, and it will be eventually adjusted up to saturation when this number here is 0, when the growth rate equals the damping rate. I did not mention that, but the quasilinear approach involves a considerable dimensionality reduction. So basically, initially the problem depends on time and 3 velocities and 3 positions. Because of this memory erasure effect that naturally emerges for marginally unstable modes, what happens in position becomes unimportant. That becomes an ignorable coordinate because you're no longer retaining information on the phase space orbits. You're forgetting the orbit shapes. So the resulting distribution function is enough to be described by velocity and time, as opposed to the full nonlinear picture, which you need time, position, and velocity. So it is a considerable dimensionality reduction. Of course, you're capturing less details, but for marginally unstable modes, I claim that those details are not that important in the first place. And the interesting feature of this reduced system here is that it retains a lot of the essential properties of the full nonlinear system, namely the saturation level and the growth rates are the same for this quasilinear regime with respect to the full nonlinear equation. Okay, so let me show comparisons with of this system of equations resonance broadened system of equations with respect to full nonlinear simulations. But before, let me show you what the diffusion coefficient looks like versus in velocity space. So what I'm plotting here, let me just go back, is this function that I just showed, the diffusion coefficient. So it is the envelope around the resonance. So this function is telling us how much diffusion you have locally as you go closer or farther away from the resonance. It's a weighted function that weights the strength of the resonant interaction. This is the plot. So basically, in the absence of any broadening, the absence of amplitude broadening or collisions, this is a delta function here. So only particles that exactly satisfy the resonance condition are the ones that are, interact with the wave in a resonant manner. What I'm showing here is what collisions do to that resonant interaction. So this is the envelope for that interaction. And those are different ratios of drag over scattering. So when drag is 0, but you do have some scattering, then this is a symmetric function around 0. So you have a broadening here that is proportional to the effective collisionality. As you increase drag over scattering, what you see is the peak of those functions is shifted to the left. So what this means is that the drag, so drag is again a dynamical friction which slows particles down in a preferential direction. So it slows particles down, never accelerates them. So that's why the peak of the resonant interaction strength shifts to the downstream in velocity. What is shown here is on the plot on the bottom is the delta F, the redistribution of particles around the resonance, and those are simulation results shown by the dashed lines versus analytical results. So the agreement is very good, but we're running the simulations in the regime that the theory is applicable, namely near marginal stability. So the drag here leads to structural changes of the distribution function. I like to use this analogy of, like, if we think, for example, of MHD without resistivity. So you have a certain number of states that can be accessible. Then you add an epsilon of resistivity that already breaks the constraints and allows the system to evolve in different ways and removes those constraints. So this is similar here. Any amount of drag allows the system to drastically change the way it wants to evolve. What happens when so here I showed results for when drag is less than scattering. What happens when drag is larger than scattering? Then something even more dramatic happens. So 0 here again is the center of the resonance. When drag is 0, then you just have a peak around that. Now, as drag over scattering increases, then not only you shift this resonance function to the left, but you start splitting the peaks of the resonant function. So physically, this means that without drag, only particles that are very close to the resonance can experience wave-particle interaction. But for large enough drag, you give the opportunity to particles far away from the resonance to still be in resonance with the wave. On the bottom is what happens to delta F, the relaxation of the distribution function. So again, we're doing only one resonance here to illustrate the point, simulation versus analytic results. And just for reference, this is what the analytic result looks like. It looks a bit ugly, but it's very easily evaluated in terms of elementary functions. Now, I showed you what happens to the distribution function. What happens to the amplitude of the wave that is self-consistently evolving with that relaxed distribution function? So what is plotted here is the wave amplitude versus time. And for different ratios of drag over scattering, you access different saturation levels. And I think it's worth noting that in general, this evolution can involve a lot of overshoots and undershoots, and the wave can oscillate and be intermittent in different ways. But again, here we are in a regime that that intermittency is killed by the fact that we're killing phase space correlations, and we're producing entropy at a faster rate because collisions are so prominent in the system here. So that's why you see the wave amplitude quasi-steadily evolving to saturation without much oscillations around that level. As we move away from marginal stability, then each of those curves would you would see like a peak and troughs, and eventually you would oscillate towards a saturation level. There are aspects of drag that I'm not covering in this presentation that have been well appreciated before. For example, in the nice works of Lily Breisman and Sharapov, they found that for high enough drag over scattering, it leads to less likelihood of, as you keep adding drag here, it will no longer evolve to a quasi-steady regime. Rather, it will evolve to the so-called chirping response, which is shown by this plot here. This is the changing, or this is a spectrogram. This is the changing frequency of the wave versus time. And you see a lot of those hooks, a lot of those bifurcations in frequency, which are different flavors of chirping, wave chirping, that is induced by drag. Not only that, drag can lead to asymmetric chirping, as you see here. What happens up north of the resonance is not the same as what happened to the south of the resonance. And in fact, just a couple of days ago, Udipan Banik and Amitav Bhattacharjee submitted a paper to arXiv in which they show another facet of drag, that in that it shows that the classic picture of the plasma echo response found by Su and Obermann in '68 can be drastically changed as drag becomes important, and more specifically, that the super exponential decay for decays in which you have only scattering changes to a more regular exponential decay at late times due to drag. That becomes more important at those times. Okay, so let me briefly touch on the applications I alluded to in the beginning. So let me first talk at how this framework of this transport framework for particle relaxation can be applicable to the dynamics of energetic particles in a tokamak. So this is a hard problem. It's very hard to model. Usually the community has been resorting to very insightful but very expensive codes that prohibits us from doing parameter scans. So having a more reduced theory that you can see the physics more transparently, even though it's only applicable in the near threshold regime, can be very useful in guiding and interpreting both simulations and experiments. So what I'm showing here is an application of this resonance broadened quasilinear system to energetic particles. So, and this new development allows us to move those quasilinear simulations from interpretive to predictive. And led by Nikolai Gorelenkov here at PPPL, we developed this resonance broadened quasilinear code that is essentially the numerical realization of the model that I just showed. It uses the eigenstructures and the eigenfrequencies of the alphenic waves as calculated by an MHD solver, and then it relaxes the distribution function of the energetic particles upon the resonant interaction with those waves. Then it feeds that diffusivity calculated by the quasilinear code to a global transport framework called TRANSP that uses those anomalous diffusivity of the wave-particle interaction to evaluate what happens globally to the energetic particles. So what I'm showing here on the right, the top plot is a D3D discharge where you see the frequency of multiple Alfvénic eigenmodes versus time. Those are called reverse shear Alfvénic eigenmodes. They also live in the gap, and they experience frequency changes on the equilibrium time scale. So we want to understand the effect that those instabilities have on the confinement of energetic particles. A good measure for that is the neutron rate. So this, you can think of this as a proxy for how many fast times are confined in the plasma. The classical prediction, meaning no waves, so when you don't have the interaction between Alfvénic waves and energetic particles, would be something along of those of this black curve. So the beam is modulated, that's why you see ups and downs here. But you would expect this type of confinement. But in reality, what is measured is the red curve here. And when we add the physics of those modes through the resonance broaden quasilinear code, then we're able to predict something much closer to the observation. Still not a perfect match, but it captures at least the order of magnitude of the confined fast times in experiments. Now, how can this be applied to the dynamics of self-gravitating systems in galaxies? Now, one outstanding problem in galaxy dynamics is what happens to the evolution of the center of galaxies. So I think around 2/3 of all galaxies have a bar structure in its center. So it's a cluster of stars here. I put this green box here just to illustrate what the bar is. So that rotates and can generate a gravitational disturbance throughout the galaxy. What I'll show you is that the framework, the transport framework that we originally derived for plasmas is to lowest order applicable to the relaxation of resonant bodies, of bodies in the galaxy that resonantly interact with the perturbation that this bar generates, the rotation of the bar generates. So in a plasma, we're normally looking at instabilities that have to do with a discrete spectrum, for example, Alfvénic waves, maybe Langmuir waves. What is the equivalent of that in galaxies would be the gravitational potential disturbance that the rotation of this bar is generating. It's a co-sinusoidal form, and the whole galaxy feels it. But most of the let's call the particles in the galaxy would feel up and down. So they would feel this disturbance and they would just adiabatically respond to that. So they would go up and down and keep oscillating as a result of that. But in the same way that in a plasma, we have a resonant subpopulation of particles that have this matching condition called the resonance, which is the platform for the wave-particle interaction. In a galaxy, you have a subpopulation of stars and dark matter bodies in the halo that revolve within a certain velocity and trajectory that it has a matching condition. The trajectory of some of those bodies has a matching condition with the disturbance generated by the rotation of the bar. And those bodies can respond resonantly to that interaction. In a plasma, we were talking about collisions coming, for example, from pitch angle scattering, and in a galaxy, there's the equivalent to that, which would be the diffusion due to non-resonant interaction, so the background. And again, to lowest order, the dynamics of the two systems is isomorphic. So in this work led by Chris Hamilton, together with Libby Thoman and Lev Arzamasky, we tried to leverage the theory originally derived from for plasmas to this context, and we tried to calculate. We calculated the torque on the bar. So basically, again, the resonant interaction is the bar generates the disturbance. A subpopulation of stars and dark matter can feel that in a resonant way and can suck energy out of the bar. So it can gain energy as a result of this perturbation. The same way as in a plasma, we have inverse Landau damping, and you have a generation of a local plateau of the distribution. So the torque on the bar can be calculated using this integral here. This is the gravitational disturbance. And we used, in a limiting case, the plasma theory for the relaxed distribution function to calculate the torque on the bar here, and therefore calculate the slowing down rate of the rotation of the bar. And what Chris found was that this plot here shows the slowing down rate of the bar, of the galactic bar, versus time in a time scale of giga-years for different collisionalities here. So for zero collisionality, asymptotically, you would find that and that's the prediction, classical prediction by Tremaine and Weinberg, 84, that whenever you have this resonant interaction, the particles would take some energy out of the bar, but eventually that would cease. So you would no longer have free energy from gradients to continue that interaction. So you would slow the bar some, but then that's it. It would continue rotating. Now, what happens in the collisional prediction? So as we add collisions, we find that there is always a residual friction on the bar. There's always a residual slowing down effect of the resonant particles on the bar. And we can understand that in a similar way as in a plasma. So if you think of inverse Landau damping in a collisionless plasma, you can take, just the usual nonlinear Landau damping in a plasma, you take energy out of the wave, you generate a local plateau of the distribution function. That's it. After you generate the plateau, there's nothing else going on. There's no more free energy. There's no more change in the wave amplitude. In galaxies, collisions also have this effect, as in a plasma, to restore the local gradients of the distribution around the resonance. So it can continuously provide more and more free energy. So the resonant interaction, in fact, never ceases. Collisions are always trying to restore the distribution function to some equilibrium state, and the resonant interaction is always trying to flatten that gradient. So the prediction for the collisional case is drastically different, is that real galactic bars will always decelerate because the slowing down friction effect of resonant particles is always there, it never stops. Collisions are always resupplying a means for that resonant interaction to continue to take place. And I think those can be very timely predictions in this Gaia observation era. So Gaia is a spacecraft that is going to measure something like around 1% of the distribution of all stars in our galaxies, both position and velocity. So eventually this type of prediction could be confronted through real observations. And they might also be used to constrain dark matter models, depending on the distribution function. Chris Hamilton gave a nice tutorial talk last APS DPP meeting, and he's writing a tutorial paper that is covering this topic as well. Okay, so let me come to my final slide, which is basically a summary and implications of the work. So the main message here is that on the theory side, is that close enough to marginal stability or an instability threshold, the nonlinear kinetic theory naturally becomes a resonance broadened quasilinear theory without any other assumption. And that's very different from a textbook quasilinear theory that usually invokes to justify the random phase approximation, it requires that you have resonance overlap from the outset, quantified by the Cherenkov criterion. That's what usually satisfies quasilinear theory. Here is very different. Collisions are playing the role of scrambling particle trajectories and making a random phase approximation better. So again, when you're near marginal stability, the wave does not grow too explosively, not too fast. So collisions have time to be in charge of the dynamics. Collisions control the dynamics, and they lead to memory erasure through this time local effect of the dynamics. Not only nonlinear theory becomes a quasi-linear theory, but also it can be satisfied by for a single mode or even a single resonance only, without the need for any resonance overlap. So that's, I believe, something that has not been appreciated before. And as I showed along the presentation, what we would like in any reduced theory is that even though it's reduced, it's cheaper to simulate, it's easier to understand. We would like that some essential features of a more complete, comprehensive theory like nonlinear would be naturally encoded in that theory, and it happens in this case. So the fundamental features of nonlinear theory, for example, saturation levels and growth timescales, are automatically built into this quasi-linear system, resonance broadened quasi-linear system. What we get, what emerges from that calculation without any assumption other than near marginal stability is the shape of the resonance, so an analytical expression for the envelope of the resonance, so basically a map for the wave particle resonance energy exchange. It shows that collisional scattering broadens the resonance, drags lead to shifting and splitting. This can be very useful in guiding and interpreting simulations, both in plasmas and in self-gravitating systems. And as I showed, those equations have been programmed into code that realistically captures the dynamics in a real tokamak, the RBQ code, in which the simulations are fully predictive and self-consistent and coupled with a global transport code, transp. And we hope that in the future, this analysis being simple enough, it could be used to do in-between shot analysis and eventually power plant design optimization through parameter scan. That's all. Thank you very much.